required. You can start from zero. Nothing is there. You can start from zero. It offers potential for significant cost and lead time reductions. When we talk about the smart manufacturing, of course, economic considerations, they are at the forefront of that. Increase the material efficiency. Each and every microgram of the material should be able to be put into engineering usage. That we call it as 100% material efficiency, which means wastage is minimal. Improve component performance, of course, that is the main target. Whatever component is made through this technique, it should be able to perform for its designated life without undergoing premature failure. So its reliability, durability, performance, etc., everything should be taken care of. The reduction of inventory and logistics caused by local or demand management. Yes. It is very simple to have storage of mandatory inventory. That means what I need to have is only the consumables that are required to make a component using this technique. Right? So that is an advantage with this technique. Now, if you see, there are a number of generative production methods for metals through which metals can be generated. So we are here broadly dividing it into two fundamental types. The first one is powder-based and the second is wire-based. As I told you earlier also, it's the feedstock that is going to categorize it, whether to categorize it under the powder-based processes or wire-based processes. Now let me tell you, if you look at the powders, if you search it on the Google, not only the cost, but the availability is also a major issue in that case. In powder-based processes, the layers are built up using molten metal powder. Like in case of powder bed fusion technique, you lay down the powder, beam comes, it melts and deposits surface, and you get your EM part. The most common method, the powder bed process, it produces extremely precise results, but is somewhat slow in production, and of course because the metal deposition rate in that case is very small. Because powders, they have to be melted, and as the powder melts, it results into deposition of that powder, but here the deposition rate is very small. So slowly we'll come to know that how is it so. Wire-based processes, on the other hand, build up the component by melting a wire-shaped filler metal. We have a filler wire whose diameter could be 1 mm, 1.2 mm, 1.6 mm, right? Requiring the use of a laser electron beam or arc. We have laser beam welding process, we have electron beam welding process, and we have conventional welding processes also. The only difference is that in case of electron beam, we need to have carefully controlled environment where vacuum is to be maintained. Because if you look at the electron beam, right, if vacuum is not used, it reflects. Now these processes have a high deposition rate and therefore help to cut production time. So which means it's not only the quality or the cost, at the same time we are also concerned about the efficiency of any EM process. WAM is a wire-based process and uses the gas metal arc welding process. Yes, largely because this is the typical or conventional working principle of a gas metal arc welding. Filler is available, it is fed into the welding arc, right? And as you move your arc along the workpiece, the wire, tip of the filler wire, it gets melted continuously, right? So what happens at the tip of the wire, droplet by droplet formation occurs, and this droplet, under the action of different forces, gravity is there, this Lorentz force is also there, pinch effect is created, right? And accordingly the drop, it detaches from the consumable tip of the filler wire and gets deposited into the molten beam. And this is how this deposition is accomplished. Then, of course, there is an issue. Depending upon the processing conditions, what would be the size of each droplet Depending upon the size, what will be its acceleration, momentum, because ultimately what is going to happen is certain mass of the droplet, it will come with certain velocity. If that is the case, kinetic energy will be associated, and that kinetic energy is converted into now thermal energy in the form of heat. Then the frequency of the detachment of droplets is different. 5 droplets per second, 100 droplets per second, 150 droplets per second, right? So that is also major consideration in this case. If you look at this, WAM offers a number of advantages besides its high deposition rate. For deposition rate, this is one figure, just to keep in mind, that the deposition rate can vary from 1 kg to 4 kg per hour. Just imagine, I've got a stool of 4 kg and in 1 hour I'm able to deposit it. No process is capable of doing that. So I have got some comparison in the next slides. So just let you know. Now, in the future, multi-wire solutions could give rise to even higher deposition rates. The equipment and material costs are also important criteria, which is another strength of WAM. All you need is a suitable welding system. Still, there is a scope of improving the productivity of this WAM process. There is no requirement for costly special equipment such as the vacuum chambers needed for the faster electron beam process. As I told you, in case of electron beam, I need to have a vacuum chamber. Then that vacuum chamber is going to pose a limitation on the size of my workpiece. I cannot go for say 2-3 meters of product through electron beam. Otherwise, I have to have elaboratively designed and developed vacuum chamber. And of course, cost is also involved. But to maintain that chamber, cost is involved here. Okay. In comparison to powder-based processes, GAN benefits from the immediate availability of a range of certified wire types. There are certain standards, right, according to which the filler wires are manufactured. I have to simply pick those wires and go for the deposition. Unlike in case of powders, unless until they are made to certain set standards, right? So that is one limitation associated with this powder-based. Yes, this is something important. If you want to venture into the area of designing and development of powders for AM products, right? So it is a bit difficult part. Like in this case, it can take years to acquire the necessary certification and to produce data sheets. Since the use of metal powder is a relatively new technology. These powders, they have to be in the atomized state. You cannot have any kind of powder, right? Then powder particle size, they have to be maintained, and once you deposit it, you have to generate the database related to that. So that is what is meant by the data sheet. So based on the data sheets, you need to convince the third party, yes, this is what we have done. Accordingly, they will examine your data and pass your this powder. And yes, we are certifying you are capable of producing such and such powder of this such and such formulation. Now this process WAM is not new. It was first patented in 1920. Electric based, when we say electric arc based, electric arc and welding arc, they are synonymous terms. EM is probably the oldest, outwardly simplest, but least talked about of the range of EM processes. This we've already covered, that welding wire has to be there in the form of a feedstock that could be utilized for deposition. Right? The process has been used to manufacture round components and pressure vessels for decades, but not until quite recently has interest in EM in general and arc-based EM in particular, it has increased. Right? That means more than 100 years of states inception, with a resolution of approximately 1 mm and deposition rate between 1 and 10 kg per hour, depending on what kind of arc source we are using. If I switch over from gas filled arc welding to solid arc welding, my deposition rate is going to increase. In what way? In case of a DAY-2 process, what we are using is how this statement goes. Yes. When I say GMAW, my feedstock ranges from diameter 1 to 1.6 mm. And of course, the deposition rate is the direct outcome of the volume of the metal that is going to be melted per unit time. If I switch over to another process, which is summit arc welding process, that is also being utilized for this purpose of AM, then look at the sizes. A typical size of 4 mm. Obviously, it is going to be on the higher side. So, metal deposition rate corresponding within the VAM itself, we have different processes, right? And outside VAM also competition is there, and within VAM also mutual competitions are there, right? So here, when we say manufacturing efficiency, deposition efficiency, or deposition rate is one important term. Some insight into what sort of equipment should be required when you have to adopt this technology. If you see, you have got, and of course, arc welding power source has to be there. Arc will be generated, but how it will be manipulated is going to be decided by what sort of, whether you are going for manual welding, whether you are going for automatic welding, right? Using some kind of manipulator like linear manipulator, or we are going to make use of some kind of a robotic arm which will have different axes so as to manipulate the arc in different directions depending upon the need of the job. Well, the potential range of manipulators is vast, but most fall into one or two types, robotic or machine tool based. I got one example, one slide related to where we have used manual mode also. Right? Similarly, there are different types of power sources available, and to some extent, the material in use will drive the arc deposition process selected. Now, if you look at this point, material has got a special consideration. That means material-centric approach is also important in this case. As this statement says, for example, titanium alloys, they are usually possibly more stable TIG or PTA, that is plasma transfer arc, whilst most of the materials are possibly with MIG or MAG equipment. So that means, depending upon the nature of the materials, you have to select the process. But yes, we have made certain attempts to use GMAW process for the purpose of creating VAM walls within a controlled time. So, and apart from this robotic based, we have machine tool based systems into which the deposition equipment has been integrated to have additional potential to allow the combination of AM and subtractive cutting also. Just imagine you are adding or depositing layers at the same time machining is also taking place. So at the same time subtractive cutting is there, allowing features to be created and finished machines that could not otherwise be possible. So this is a combination of both. There are laser or powder based combination AM or subtractive machines available. Development of arc based system is underway, and it is now only a matter of time before a system is brought to market. So this is an important point to be seen here, that there is a potential to look into this aspect, that is it possible to have this thing in the hybrid mode. You are depositing the material, at the same time you are also allowing the machining to take place.
It's like that.
As I told you, there is going to be an interaction between the filler wire and the electric arc. So that means now there are certain special considerations with regard to what type of alloys we want to deposit. You can see here, carbon low alloy seals, stainless steel, and aluminum alloys. For many of these materials, the deposit properties are similar to those expected from a weld metal in a joint. So that means in case of conventional welding, what we do is we join two pieces together, put them in a certain configuration with a certain joint, remove the welding arc onto that, and what you get is the weld joint is accomplished. The properties associated with the weld metal are similar to what we usually get into EM. EM is what basically all weld metal, depositing layer by layer, right? But there are certain notable exceptions also. If you look at this, aluminium magnesium series of alloys, which are also known as precipitation strengthening alloys, then titanium alloy TI6, EL4V. So these are some notable exceptions. Right? If I try to match the properties of the welded joints for these base materials, they would be different from what we get under VAM using these materials. RPSTM has significant potential for cost and lead time reduction for medium to large engineering components of medium complexity. Now look at this definition. Some other terms are also being included here now. Previously we talked about only the manufacturing efficiency, engineering performance of the components, but here what you see is, of course, cost consideration is important, lead time reduction is equally important. And apart from that, looking at the limitations of the, or the, say, not only limitations, but the advantages of this process. It is possible to have engineering components fabricated whose size would vary from medium to large. Then, lastly, what sort of complexity is associated with that part? What are the tolerances that would be available to you? You have to fabricate that or print that component. Careful design for RBCM can enable partial topological optimization and careful selection of wire feedstock. You can make added material optimization and multi-material components possible. I will take one live example from our own research initiatives that how we have gone ahead with the multi-material deposits, which have proved to perform better in certain harsh conditions. If EM is combined with a machining platform, why do we require machining? Because that is one important requirement, because in case of VAM, the surface finish is not that good. You have to remove an envelope of around 1 mm from each side so as to achieve the desired surface finish. So that's why you have to integrate AM with the machining platform. It becomes possible to create some otherwise impossible shapes. RPSTM is not a net shape or automated process at this time. The surface finish, because waviness is there, usually means the part must be finished machined. If you look at the fundamentals of the process, drop by drop melting occurs, it gets deposited on the previously laid down bead. Droplet comes, it has to deposit. Right? While it deposits, there is no, you can say, kind of pressure from both the sides. It deposits on its own, and while it does so, the surface finish is not that good. The part model must be interpreted and the manufacturing process manually prepared. So that is a huge challenge. If you look at this, on one side we are talking about immediate benefits, area of applications, right? To what extent the component sizes can be reached, what sort of complexity can be achieved. At the same time, this is one you can say feature which needs to be looked into, that we are still managing with the this. There is no dedicated software. Yes, machines are inbuilt, giving you the programming also, programmed power sources are there, but as far as the entire manufacturing sequence is concerned, that should be manually controlled by our robotic setups. Now, up to this point, what we understand about VAM is, yes, power source is there to match the feedstock which is available in the form of a wire. And depending upon the power source, there is a range of parameters which can be used to match that wire. Right? When we talk about range, that means main controller. variables. That means I can make use of certain variables, like in case of a typical or conventional welding power source, we have got wire feed rate, proportionally we have got welding current, then we have welding speed, welding voltage, then your what is the angle between the wire and the workpiece, right? Then what is the position in which AM is being carried out? This is the flat position, this is the vertically down position, vertically up position, this is the overhead position. So that kind of flexibility is there, right? And the most comfortable, the easiest of all this is the flat position, which is usually done here. If I change my process variable from X to Y, the deposition rate associated with the wire would change. If I go for the higher welding current, melting rate of the wire would be increased, right? If I slow down my welding speed, the deposit per unit time will be more in that case. Which means I'll be able to get thicker deposits if the welding speed is slow. If I increase the speed, those deposits they will be thin. So that is the role of the process variables in this case. All the process variables combine to produce deposit bead geometry, and it is manipulation of this bead that results in the desired confirmation. So next, full control of the process variable so as to have the desired outcome in terms of having the product or the component or the wall of certain thickness, certain height. Unfortunately, and unlike welding, bead geometry is affected by more than just the deposition parameter. The residual, because in case of welding, what we do is at the most we can go for single pass, double pass, 3 pass, 4 pass, 5 pass, but here you might have to go for 100 passes also. Right? So that poses us an issue of heat management. How will you manage the heat as you move up? Right? Heat management issues are encountered. So that's why it is unlike welding and unfortunately. Right? Heat geometry is affected by more than just the deposition parameters. The residual heat as the part is built results into a continuously changing thermal field that must be accounted for if a deposit layer is to be accurate and free from defects. Now, if some kind of deformation occurs in the, say, your component that is visible to me, through visual inspection, I can make out that something is not in conformance with the desired geometry, but as far as residual stresses are concerned, it is very difficult to predict. With the naked eye or with the visual inspection, I cannot judge or predict what kind of residual stresses would be built. Now, if I look at the implication of the residual stresses, we are talking about the residual heat. That means some portion of the heat is already retained in the previously deposited beads. Because it will take certain amount of time to get the entire heat dissipated to the surroundings. Right? Simply speaking, what happens is, if I lay down a bead, 3 modes of heat transfer are involved here. One is conduction, it is getting conducted through the base material. Next is convection, and the third is, if I heat the material, if I deposit a bead, I take my bare hand near to the bead, I will start feeling the heat of the bead. So through convective mode of heat transfer, it means heat is being convected from the bead. If I touch the bottom plate or the base plate, again I cannot touch it with the bare hand. That means heat is being conducted through the base plates. Then we cannot see with the naked eye. These are the radiations. So radiation is also involved. But just imagine when I plan to print a part with 100 number of layers, that is I am at the 30th layer. When I have to go for the 31st layer, I need to control precisely that what should be the temperature associated with the 30th bead now prior to depositing of the 31st pass. So that kind of micromanagement related to heat is required. And of course, when we say residual heat is to be managed, one major challenge that is associated here is generation of residual stresses into your component. Residual stresses means when everything is relieved, still there is a certain level of stress into your component that continues to reside within that deposit. And having residual stresses in any component is not a good thing to happen as far as performance of that component is concerned. In what way? Because your component is already in the pre-stress state. If we talk about your residual stresses. So the residual stresses are going to add up to the working stress of your component. When you design any component, right, you have your working stress, then you have your theoretical stress. To that through your design, you have certain factor of safety, so you have to work out that what would be the working stress of that component. So in this case, if residual stresses are already there into your component, they are going to say affect the service performance of that component adversely. That means component is already in a pre-stress state, and onto that you are also imposing the working stresses. And in a way, your factor of safety is going to be compromised in that case, and you might end up with certain pre-meter failures. So before it enjoys its designated life, you might end up with component as a failure. Nothing has gone wrong with the quality of the component. Everything was fair, everything was fine, radiographic quality was there, denser parts were there, no porosity issues, no deformations were there. But the only issue was that the residual stresses could not be maintained to below certain level. So that is one, you can say, wampish character of the residual stresses which needs to be looked into. And that is the reason lot of research efforts have gone into predicting the residual stresses in such components. And that is also really area of research. Okay. And of course, we have to be very accurate in depositing our layer. It should be free from any kind of noticeable defects. As parts become more complex, the programmed path of each layer becomes significantly more so. Of course, that would have come to the complication. It is really possible to strike an electric arc at the beginning of a layer and extinguish it at the end. Now that is a real challenge. Just imagine I'm going to deposit a layer of half a meter length. Every subsequent layer is going to involve certain repetitive cycles. I have to generate the arc, take it to the last point, then the arc has to extinguish. Or at the most, what I can do is, my limitation is I cannot bring that arc in the on position by for the next subsequent layer. Why so? As I told you, residual heat built up in the previously deposited layer will not allow me to do so. I cannot pressurize my this technique to complete the job in time and ending up with a rejected job. Right? So we have to be very patient, very cool, very systematic, very calculating. And once the arc starts, after traversing half a meter of the path, it has to extinguish. And as per my procedure, whether to start from there, then come back to this, or again bring my arc back to this point, that means starting and terminating point, they are the same every when every bead is laid out. So it is rarely possible to strike an electric arc at the beginning of layer and extinguish it at the end. Most layers consist of several sub-shapes which are programmed and deposited separately but joined together. Imagine I am programming my welding robot to go in order to avoid the residual heat built up into the previously processed layer. I need to maintain that interconstant. That means, let's say, this is my first layer, this is my second layer, because the only is the latent heat of fusion has to liberate away, goes away. You don't have to wait for the solidification to occur. It is very rapid. As you are depositing, as you are measuring for any solidification to occur. So it is instantaneous time. If you look at inert gases or its mixture, so as to avoid any sort of contamination into the degree centigrade, not is time to go for the next. Otherwise, what will happen? सॉरी साहब मैं करा कॉल में लेक्चर चल रहा है शॉर्ट टर्म मैं हाँ कर देने नोटिस मेल देख लेंगे ओके थैंक यू so this again is a mandatory consideration if we have to control the residual heat built up into the deposit. So what we do in that case is with the help of your thermal chart markings or with the help of you can say gun you can see the temperature. Once the temperature comes up to 150 degrees centigrade, right, it's time to go for the next week. So that is one component which will add to your delay time. Product completion times, they will be delayed, but that is a necessity. Right? Otherwise, distortion effects will be coming into picture. Then we benefits of manufacturing. So almost we have covered each and everything, but just something important is raising. Unlike powder bed feeding and machines which have a limited weight and bulk, the robotic arm of VAM machine has more freedom of movement. That means size of the component is not limited by space. It is the capability or the range of my welding robot's arm. If it is having 1 meter range, I can produce the components of 1 meter length. If it is 2 meter range, 3 meter range, depending upon the movement of the robotic arm. Okay. Cheaper process and materials, of course, in terms of material cost also, in terms of the power source also. Right? So that means inherently there are two components associated with AM processes. One is the main machine or the power source that would be used, and another is the feed stock. So these are one of the you can say these are the beneficial features associated with the AM process. Material cost is also on the lower side. At the same time, I can get my work done within 30 lakhs robotic system instead of investing 3.5 crores for a powder bed feeding machine. So initial or the capital cost is less. So in that case, there is a question for going for machining also. I don't mind. My initial cost is less, working cost is less. I can opt for the machining, subsequent machining operations also. Still, I'll be on the profitable side. Okay. Almost high quality parts. I will give you a few examples where you will see that yes, it is possible to achieve high quality pertaining to these engineering components or parts. Parts produced with them are particularly notable for their high density and strong mechanical properties, which are comparable to parts manufactured with traditional manufacturing methods. When we talk about the traditional manufacturing methods, we mean it is a rolled product, it is a casting, it is a forged product, it is a machine product. So properties associated with the traditional machining methods, they act as a reference for us when you are using other technique. Is it possible to reach the range of those mechanical properties? When we talk about the density here, if you compare a powder bed fabricated part versus VAM, you look at any publication where the researchers they have opted for powder bed fusion, they will simply account for every reason leading to lower mechanical properties would be attributable to the presence of porosity. Right? Pertaining to powder base, whereas in case of VAM, you do not use powders, you are using a denser part. Your wire is in the solid form. Right? So there is no question of porosity area, and hence the reason we call it as a high density component process. And of course, strong mechanical properties comparable to those of traditional machining manufacturing methods. Yes, it is written out here. As the wire stock is 100% dense material, there is residual porosity induced in the fabrication process, leading to a very dense iron. Right? And besides this printing new components, it is possible to opt for the repair work also. So VAM has that benefit of offering its service for repair operations also. If you see here, it's a good option for repair and maintenance operations for specific components like turbine blades. If something wears out, turbine blade wears out, what do? Do we go for the entire blade change? No. Right? So what we do is, with the use of this process, this technique, we can deposit a layer of that particular alloy onto that matching compatibility. Then we can machine that. So what you get is 100% restoration of your turbine blade with almost the same service life guaranteed. Because service life is going to affected by what? The properties. Properties are dependent upon the microstructure. Microstructure is further dependent upon the processing condition. When you are able to restore the original condition of that turbine blade, and of course, VAM has done its contribution for the RTAM work. Right? And besides that, worn out features or damaged parts can be repaired with VAM by depositing new material onto its surface. So not only the turbine blade material, if you think that there is certain portion on the turbine blade which is giving you trouble every time, right? Let us say. So let us say something is going wrong at this. This is the portion which time and again wears out. So that is the cause of concern. So I can think of having a strategy in place where I can repair this blade with a superior material also. For example, this is 316L grade. I can think of opting for some super alloy like in corner. Here, I can go first. Whose corrosion resistant, whose wear resistant would be relatively high as compared to that of 316L. So which means VAM in a way is capable of extracting the beneficial features of a superior material and incorporate the same to the otherwise inferior material in the form of reinforcement. So this mode we call it as reinforcement via superior filler addition into the worn out components. So that means VAM have got two phases now. You can fabricate and print new components at the same time. You can also repair the worn out components and make them perform better than the originally designed performs indexes. Yeah. Okay. This can result in significant cost savings. Okay. Now, up to this point, we can confidently say yes, VAM has given us this confidence that we can fabricate, we can print parts whose properties are not going to be less than the traditionally available manufacturing method. Right? Then another slide which is devoted to the advantages associated with VAM. Large size, I just told you, is the reach or the range of the arm of the roller, which is going to decide about the size. Additional design freedom is also there. You can add complexity to the shapes also. Right? So when we say this is one shape, another shape, right? So look at this more simplified shape. Then you can go for these shapes also. So complexity is also possible depending upon the model you are using here. Low startup cost, as I told you earlier, one typical example, 3.5 crore 3D metal printer plus additional cost of the powders, which might cost me around say rupees 20 or 25 or 30,000 per kg. And at the same time, the wire costing me around say rupees 10,000, right? Almost half the price of that. Then the capital expenditure 3.5 crore versus 30 lakh. Right? So all these are important considerations. Then wide material availability. You think of any composition, have the feedstock in place, you can have that alloy printed. Then hybrid manufacturing. Yes, it is possible to have the VAM in place at the same time. We can opt for laser also. So as to increase the deposition rate also. We call it as hybrid manufacturing, combined materials. Right? I'll be talking about these components. We call it as FGMs. functionally graded materials, the need and importance of these functionally graded materials. Like one example is cobalt alloy, SLIET 6. It has got high hardness, high temperature, wear resistance properties. If you look at the valve seats, you have SLIET 6 added onto that. It can withstand a temperature of the order of 300 degrees centigrade, right, for longer durations. Right? You can weld it with orthotic stainless steel. So that is the beauty of the process, that you can use combined materials. But just imagine, analogous to this, you are going to now operate a facility with powder bed fusions. What you would be doing is, how do you control the two powder? SLIET powder and orthotic stainless steel 316 cell powder. In what proportion they are going to be fed into the your laser beam? That is a bit difficult task. In this case, what we have to do is, we deposit 316 cell layers onto that, use now SLIET 6,